Continuing to talk about valence bond theory, let's now focus on multiple bonds. So, where do the extra electron pairs for the multiple bonds actually go? So they're not in hybridized orbitals at all. Those are just going to create our first bonds to other atoms. And if you remember from Vesper theory, when we're talking about how things arrange themselves around that central atom, we said to not worry about if there's a double or a triple bond at all because it's not going to impact the overall geometry. It's really just the repulsion of that ball of electron density with other electron groups around it. So, in our picture of valence bond theory, we're going to see why it doesn't actually have an impact because it's our hybridized orbitals that are building the geometry of our structure. And they're really going to account for our first set of bonds. And then our multiple bonds on top of it are going to be accounted for by the unfilled or the non hybridized orbitals, the atomic orbitals that still exist for that atom. And so we see then that there's two types of bonds that arise but from orbital overlap. And the first one we call sigma, and we abbreviate it with this symbol right here, this little sigma symbol. So sigma bonds are going to result from the overlap of atomic orbitals or hybridized orbitals that are pointing at each other along the same axis. And this usually accounts for the first bond between two atoms. And so here, if I brought together two s orbitals like this, I would form this bonding orbital that kind of came right on. I can also think about this as two p orbitals coming along or two hybridized orbitals and these two overlapping as well. As long as they're coming head on, that they're directly overlapping with each other. Now, a pi bond's going to result when we have overlapping bonding atomic orbitals that are actually parallel to each other um, rather than um, rather than coming at each other head on. They're perpendicular to the axis that's connecting the two atoms, and they're parallel to one another, approaching each other like this. And that's going to create our second bonds and our third bonds between two elements. And so here's an example of a pi bond right here, where we have, and it's really looking at two, let's say, p orbitals coming together and overlapping here and here, but it won't overlap at that node, right? And so it creates a pi bond that looks like this, or pi bonding orbital. So here are some examples of the sigma bonds. Um, and so we have the kind of two different ways you can form, or sorry, the three different ways you can form a sigma bond. You can overlap two s orbitals like this, and they'll come together and like Venn diagrams create this kind of structure right here. You can also bring two p orbitals together, but they're going to have to be along the same axis. So they have their lobes overlap right here. And so these are two p orbitals that can form a sigma bond. And when you bring them together, they would have more electron density in the middle of the two nodes of the two p orbitals. And then we can also think about this for hybridized orbitals. So here are two sp hybridized orbitals, but it could be sp2 or sp3. It's just saying two of our hybridized orbitals are coming together. And as long as they're coming together, overlapping in the same orientation on the same axis, then we're going to see something that's really similar to what happens with the p orbitals, right? And except it's going to have even more electron density around the in between the two nodes at the nucleus for the for the hybridized bonds. And so all of these represent sigma bonds, and they're typically that first bond that is created between two elements. And we can have different combinations too. Like we can have an s orbital combined with a p or with an sp hybridized orbital as a sigma bond. And then we get something that's like this. And that would be a s overlapping with an sp hybridized orbital. So there's a lot of possibilities. And that looks really different from pi bonds. Pi bonds are coming, instead of head on along the same axis, they're coming like this. And so remember, when we're drawing these p orbitals, these are both p orbitals, we really have a different phase after the node, right? And so I'm going to come in and color this to show the two phases as well. There we go. And so when we bring our two p orbitals together and they start to overlap, we'll have these two lobes that are in phase overlap, and the two that are in out of phase overlap as well. And we'll create this kind of picture that we see here of a pi bond. And so these are going to be made with p atomic orbitals, rather than hybridized orbitals. And they kind of create this structure right here where there's still that node that's actually along the bond axis, and then we have electron density on either side of that node. And here's what this looks like when we put it together. So this is C2H2. So we've got C2H4. So it looks like this. So we expect them to be 120 degrees for a bond angle between our elements. And we have for each carbon, it's going to be bonded to 1, 2, 3 things. So we're going to have 3 bonding domains, which tells us that we really need to build 3 bonding orbitals from our atomic orbitals. So I need to build an sp squared hybridized bonding orbitals from my atomic orbitals. And that's right here. So here's that picture of my sp3 hybridized carbon. So it takes 2 of the p orbitals and 1 of the s orbital, and it combined them to form these 3 hybridized orbitals. And then what's left is the 1 p orbital, atomic orbital, that's also present. And so when these bond together, what we have is we have one of our hybridized orbitals overlaps with a hydrogen s orbital. Our other hybridized orbital on carbon overlaps with another hydrogen s orbital. And that third hybridized orbital is going to overlap with a hybridized orbital with the other carbon. And so that's going to overlap right here. And that's creating the first bond, between the carbon and the carbon. And then once that bond's created, we have these 2 p orbitals right here, right? Well, those 2 p orbitals here kind of brought out with getting rid of all the other information. So they're going to be lined up close to each other because there's this sp orbital creating a sigma bond. So it's brought the nuclei close together. So it's brought these p orbitals close together. And when that happens, if they're in phase, they're going to be able to overlap. And that overlap is right here. That's the pi bond. That's the second bond between the 2 carbons. And so that's how we create it. And that's why it doesn't affect the geometry, because it's not a hybridized orbital that's creating the second bond. Let's look at it with 3 bonds. All right, so here's C2H2. So this is, oh, I've got it drawn. There we go. So here we go, right there. So looking at this one, we are going to have a carbon bonded to 2 things, right? So I'm going to need 2 bonding domains or orbitals. So that means I'm going to need it to be sp hybridized. So that sp hybridized carbon is going to have these 2 hybridized orbitals, but it'll still have, remember when we think about our s and our p, if I'm just taking these 2 to create my sp hybridized orbitals, I still have, 2 p orbitals left. So these become these. And they're going to be on the carbon in 2 different axes. So one might be along the z, the other may be along the x. And so as we create that sigma bond, so here the carbon, one of our hybridized orbitals creates a sigma bond with a hydrogen. The other one's going to create a sigma bond with the other carbon. And so that's our first bond. And then my 2 sets of p orbitals are going to be able to overlap that are in the same axis. And so I'll have these ones right here on the top and the bottom. They're going to become my second bond. And then I'm going to have this other set right here in the front and in the back. This is going to become another pi bond that's really going to be the third bond. And so these p atomic orbitals are creating the multiple bonds. and not impacting my geometry, but impacting the electronics of this molecule.